Hello everyone, welcome back or welcome if you're new to this YouTube channel. Today we'll be talking about something very interesting about velocity selector. So velocity selector is actually a subtopic under the topic of electromagnetism in A2 Cambridge Physics. So today we'll be briefly talking about it on how velocity selector works. So what is actually velocity selector? So velocity selector is actually a device that only allows charged particles with a specific velocity to pass through. The name velocity selector itself means that a charge with a selective velocity that can only pass through this slit, only selective of it. So this device is set up where we have a uniform magnetic field and electric field as well. So we have a source here. This source actually produces electrons with different speeds. So some electrons will deflect towards the positive plate, some will deflect towards the negative plate, while the rest will pass through this region or pass through undeflected. Now, how all these three phenomena works, I will explain to you in a while. Okay, now we have uniform magnetic field and I have drawn X here. X means the magnetic field is actually into the page. Okay, X means magnetic field is into the page. If it's a dot, that means the magnetic field is out of the page. So if you find it difficult to identify, like you get confused easily whether X means in or dot means out, okay, here's a video for you to make your life easier and to know whether X means in or dot means out. So let's watch the video together. Okay, so a tip to know whether magnetic field is pointing inwards or outwards, whether X is in or dot means out. Here's a tip. You take your hand, okay, just make a fist with the thumb out. So when the thumb is pointing towards you, you can see like it's like a dot coming towards you, So this means magnetic field is pointing towards you, pointing outside. Now you turn your hand. Can you see a X? And where's the thumb pointing? Inside, right? So if it's this way, inside, that means magnetic field is towards the page. Here, the dot is outside the page. Here, the X means into the page. Okay? Alright, so I hope this clears your mind and it makes you less confused or not confused at all anymore. So you know X means in and dot means out of the page. Alright, okay. So that's about magnetic field. How about electric field? So electric field, we know, is actually from positive to negative. So your electric field is actually pointing downwards from the positive to the negative. Like that. Okay. So now, for simplicity, I'm going to use one electron to explain first. Okay. Alright. Now, let's talk about forces. We have magnetic field. We have an electron. So, if the electron is moving this way, where will your forces be? How can we identify it? We can use Fleming's left-hand rule. So Fleming's left-hand rule, you can use it when you are provided with a magnetic field and current and you want to produce a force. So in this case, we are provided with magnetic field here. We are provided with current. Wait, where is the current? We don't have current here though. Can we find? Of course we can. Your electron is moving in this direction. That means your current will move in the opposite direction. Because we know conventional current moves in the opposite direction of electron. That's how the circuit works, right? So we have our current, we have our magnetic field. Now we want to find our force. Just a side note, how about Fleming's right-hand rule? So Fleming's right-hand rule is used when you are provided with magnetic field and you are provided with the magnetic force and you want to find induced current, which is not what we want. We don't want induced current and we don't have a force to begin with. We want to find the force. So our best rule to use is Fleming's left-hand rule. Okay. Now, take out your left hand and watch the next video to know how do we proceed with this. Alright, now we are going to apply Fleming's left-hand rule. Make sure you take out your left hand. Okay, make sure it's left and not right. Okay, so take your hand and do this type of posture. Okay, now your thumb is your force. Your index finger here, your index finger is your magnetic field. Your middle finger is your current. F, B, I. Force, magnetic field, current. Okay. So based on what we have seen just now, we are going to find the force because provided that we have given magnetic field and the current. So this is magnetic field, right? So where is our magnetic field pointed? As you have seen just now, magnetic field pointed is actually pointed into the page. So it's inside. This is how your hand should be. It should be inside. Into. Where is the current? The current is in the opposite direction of the electron, right? The electron is moving this way. But, like we have said, conventional current will move in the opposite direction of the electron. So this is your current, right? Your current is moving this way. It's moving this way. Your magnetic field is still into the page. Your current is now this way. Now where is your force? Your force is downwards. So that means your magnetic force is downwards. I repeat, your hand was initially like this. Magnetic field is into the page. Current is in the opposite direction. Where's your force? Downwards. So your magnetic force is pointing downwards. This is how you use your Fleming's left-hand rule. Alright? So from the video earlier, we can know that, I'm going to put your electron here in the middle. Our magnetic force is pointing downwards. Right? Now, how about electric force? Our electric force is actually pointed upwards. Whoa. Why is it upwards now? Because electron is negatively charged. Am I right? So negatively charged will attract to which plate? The positive plate. So your electron will actually move this way. Not to say move, it's attracted to the positive plate. Therefore, your electric force will be upwards. If let's say, if let's say this was a positive particle, not positive electron, yeah? Positive particle, where will your electric field be? If let's say here is positive and here is negative. Let's say your field here is positive and here is negative. Where will your electric force be? It will be downwards instead. Because, why? Positive is attracted by negative. Same goes here. That is why your electric force is upwards. So the idea is that when the electric force and magnetic force are equal and opposite to each other, the net force is 0. So from here, we can write a formula. Because when they're equal and opposite, we can actually equate them together, right? Magnetic force equals to the electric force. We know magnetic force for a particle, we have a formula of BQV. And for electric field, it's EQ. So we can cut out the charge, the Q. So our V is actually E over B. So that means by using this velocity selector, only electrons with the speed E over B are able to pass through these slits undeflected. So, we have covered the first case. So, when your velocity of the electron is E over B, it will pass through undeflected. It will go straight. Now, let's look at the rest two cases. What if it goes up? What if it goes up? Okay, let me change the color. What if it goes up? If it goes up, that means the electric force is more than the magnetic force, because you are more inclined towards the positive plate. That means your electric force is getting higher. That means you are more attracted upwards. So your electric force is greater than your magnetic force. Can we talk about velocity here? Of course, because we know magnetic field from this formula. Magnetic field is dependent with velocity. Why? Because FB equals to BQV. Your magnetic field is dependent to your velocity. So, based on this, as the electron deflected upwards towards the positive plate, our magnetic force decreases. That means our velocity of the electron is less than the velocity of the velocity selector, or less than the required velocity needed to pass through the slit. Okay, because from this formula, if magnetic force decreases, velocity decreases. It's a directly proportional. So this is the case when it's deflected upwards. What if it deflected downwards instead, towards the negative plate? If it deflected downwards, it means the magnetic force is more than the electric force. How about the velocity? When the magnetic force increases, the velocity will also increase, right? That means the velocity of the electron is greater than the required velocity needed to pass through the slits here. So this is when it deflected downwards. Okay, let me write when it goes straight. Okay, when it goes undeflected, what happens is your magnetic force is equal to your electric force, because they are equal and opposite. So they will remain undeflected and they will pass through the slit nicely. So this is exactly how velocity selector works. Simple as that, right? Okay, so few key points that you need to know. Okay, I will highlight the key points here. Okay, few key points. First thing, we have a 3 scenario. First scenario is when it deflects upwards. You need to know which is greater, which force is greater, and what is the velocity. Second scenario is when it deflects downward. Third scenario, which is the most famous one, is when it remains undeflected and it passed through the slits. What is the velocity? If let's say they ask what is the velocity that will pass through the slit undeflected, this is your velocity. And this velocity is called as the velocity selector. People usually denote this as Vs to show that it's the velocity from the velocity selector. The name itself, velocity selector, so electron with this specific selective velocity will only be to pass through undeflected. So that's about it for today's video. I hope you are clear now on how velocity selector works. I'll see you in the next video. Thank you for watching, and let me know if there are any other topics that you would want me to discuss. Thank you. I'll see you soon. Bye bye.